Okay, so far, chapter 16 was about normal distribution. Yeah, so you had a nice normal curve, it's symmetrical. 16E finishes off at a nice sort of simple idea or a concept, and it's one that there's a property that you should know and write in your bound reference. I don't think it comes up in your formula sheet here. But normal distribution, for what type of data do you use it for again? Discrete or continuous? Normal
distribution.
I thought you were.
No, I was thinking about binomial.
That's right. I thought you were doing a sarcastic comment there. But yes, it is continuous. Now, because it's continuous data, in this exercise, we're going to be looking, well, can you use, when you have a discrete, can you use normal, which is a continuous data calculation, can you use normal to approximate for discrete? Yes, you can. You can use a normal data to approximate for a discrete data, but there's a particular situation. And that situation is when the sample size or the population, it's large. The larger your group is, and this is a great visual aspect to it. If we only do a couple of binomial, so discrete, 1, 0, 1, 2, 3, 4, 5, 6, you can see it kind of looks, but not really a normal distribution. But you can see as I increase the size, 10 to 10, you can see that it's starting to change as I increase from 10 to 20, 20 to 50, and then 50 to 100. So the theoretical point is that what if I start doing it to 100,000? If I made it really large, more trials in a binomial or discrete situation, if I do many, many trials, it kind of looks like, even though the probability was 0.2, so it's skewed, this is negative, or this is positively skewed, symmetrical, negatively skewed. But what happens is actually it tends to become symmetrical about what the probability is. So if it was 0.2, 0.2 of 100 would be 20. So you expect it all at 20, which is over here. You can see there. Whereas over here, probability is 0.5. Then 0.5 of 100, you expect most of your data starts to sit at 50. And then same thing with 0.8. Most of your data, 0.8 of 100, most of your data sits around the 80 mark. So what are we seeing here is that the larger the number, it seems that it looks a bit more symmetrical. And because it looks more symmetrical, that means it's got properties of a normal distribution, right? So here's the property that I want you to have in your bound reference, or just at least an FYI fact. When can you do a normal approximation to a binomial distribution? It's when, and in your textbooks they say this, although I think sometimes they say greater than equal to 10, but in your textbooks it says greater than 5. Okay, so if you took n times p, which is the mean, n times p, and then you did n times p times the chance of not getting what you want, that's your variance there. You times those values, both your mean and your variance, if it is greater than 5, you can use that. Okay, so that's the first thing. So greater than 5, if your mean and your variance is greater than 5, then you can use normal approximation. Because remember, normal, the property is when a function is distributed normally, we have the mean and then the variance. Okay? If those two are greater than 5, we can then do that approximation. So normal approximation for a binomial. Okay? So here's an example. So if n is large enough and the skew is not too great, okay, the normal distribution can be used as an approximation. So let's see. Here we have, in a city in the US, 60% of adults have a full-time job. Okay? A random sample of size 400. So that's a large one. Sample size. So n equals 400. Sample size of 400 adults is taken. Now, the first part of the question is, when you're seeing these type of questions, you got to ask that first type of question. You say, well, is it a normal approximation? Can I actually use an approximation for this? And if I can, what do I need to prove? Mean. N times P. N is 400. What's my P? What's the probability of picking an adult with a full-time job? 0.6, because 60%. So 400 times 0.6. I don't know what that is. What's that? Let's do 400 times 0.6. I get 240. Then what's my variance? Which is sigma squared. Variance is N times P times 1 minus P. It's 400 times 0.6. Yes, 240 times 0.4. What does that give me? 0.4. 96, yes. So variance is 96. Are they both greater than 5? Yes, they are. And because they are, based on this property over here, we're saying since NP and NP, 1 minus P, is greater than 5, therefore, you can use normal prox. Okay? Yes?
Is there a reason that's 5? Is it just like a number that sort of just works for?
It's a number that has shown that the distribution is large enough.
Okay.
Yeah, because ideally the binomial has to generally look more symmetrical,
Yeah.
and it finds that at that particular level, that's when it happens. Okay. Sometimes it's 10. I've seen it in more like other American textbooks, but for us, in our VCE system, it's greater than 5. Yeah. Yeah.
When you like the, can you use that notation there, like the x's?
This one? Distributed? Yeah. Oh, you're trying to prove it.
Like once you prove it, you say since that is greater than 5, then you say x.
Yes. Yes. For the next bit. Yeah. For the next bits, yeah. All right, so find the variance. We already know the variance was already calculated. Ryan told us before, variance of x in this case would be 96. Okay, because that's your NP times 1 minus P. All of that is just coming from your your binomial. Yeah, so if you're wondering where NP and all that is, that's your binomial properties. Okay, that's chapter 14. All right, now you got your variance. Let's actually prove that if you did it binomially and you did it normally, does it actually come out to be about the same? Because we're using an approximation, right? So, I just got Joe shake his head. Let's see. We've got, find the probability that between 230 and 250 adults have full-time jobs. So if we're doing binomial distribution, X is distributed binomially. N, which is, what is N again? 400? P, which is 0.6. Okay, so NP. You don't have to write the N equals P because I'm just reminding you what goes first. All right, how do we calculate it? We're doing essentially the probability of X, which is our random variable. We want it from 230 to 250. This is a binom CDF on your calculator. Okay, so on your calculator, we're going to use binom CDF. We know N, we know P, and we know our lower bound and upper bound. So here we go. Let's go to our CAS menu, probability, distribution, and binom, not PDF, but CDF, because we're accumulating between 230 to 250. Number of trials, 400. Probability of success is 0.6. 230 to 250, and I get about 0.7161. So that was, just writing it again, that was 400, 0.6, 230 to 250. That approximated to 0.7161. Let's take the next few digits, 48. All right, let's try now normal approximation. Okay, so you only use normal approximation when they actually ask you to do an approximation. So they'll say approximately or normally approximated to. Here we go. Again, X is now distributed normally, and again, it's 400. But our variance was 96. Okay, so mean and variance there. We are still finding the same thing. Here's our normal distribution. Wait, sorry, that's mean. Whoops. What's our mean again? 240, thank you. 240. So mean is 240. Standard deviation is the square root of 96. Let's actually write it in. Standard deviation is equal to the root of 96. So when we're doing normal calculations, we're looking between 230 to 250. So we're asking, what is the area between 230 and 250? And we've learnt so far in chapter 16 to find the area, it is the probability. And the probability, to work this out, we use norm CDF. So we're looking for the probability of X, this is X distribution, between 230 and 250. So norm CDF, we've got a lower bound, upper bound, and remember norm CDF, you need the mean and standard deviation, not the variance. So here we go back to our CAS, menu 5, 5, norm CDF. Lower bound's 230, upper bound's 250, mean was 240, and standard deviation was square root of 96. So I'm just going to do root 96, like that. Just type it in. So here we go. We do norm CDF of 230 lower bound, 250 upper bound. Mean is 240, so I'm going to write mean here, and standard deviation was root 96. Okay, so this is what I'm writing so far. And what do we get? Was it approximately? All right, 0.69256. 580. Okay, remember this is an approximation, and there's a couple of things because the difference between continuous and discrete is very countable. Continuous, because it's over an interval, it may lose out even just one little bit makes a difference. So all I have to do, even if I wanted to show that within roughly the same interval, if it was just 1 unit difference, I could have done it like this. I could have done the interval from say 229.5 to 250.5, and it should be even closer approximation to it. See that? So it gets really close, and it's because its continuity has that slight difference between how you count it, how you count the data. So yes, it was 230, 250, looks a bit off, but really the intervals could have been, I could have done it 0.1 of a difference just to make it a bit more approximated. I just went 0.5 up and 0.5 down, that's 1 unit difference there. And you can see that approximation is much closer. So this is showing that yes, you can use a normal approximation for a binomial, knowing that the endpoints are going to be affected. But the key property to take away today is that one. Okay, so NP, mean, and the variance, if it's greater than 5, you can use normal approximation.
What does it mean that like as you adjust it, like it gets closer and it's a number? What does that mean?
It's because when you're counting 230 and 250, because it's going in intervals of integers, the discrete usually, when you try to approximate using a continuity, because it's an interval, the problem with intervals is that whether you include the number or you don't include the number, it's the same thing. The answer's still the same. But in discrete it matters whether you include it or you don't include it. And because the intervals, it can be the same whether you include or don't include, often it can be slightly under what it actually should be. Well, because of that, that's why I just took a unit extra, just to get out of that boundary so that we include, it's more likely to include the 230 and the 250 that wasn't potentially included. Because whether it's equal to or not equal to, it doesn't matter, because the exact point doesn't get actually included. So if you did a normal continuum, and I said, to find the probability of x equals 230, you don't get anything. But if you did it in binomial, you do get something. And that problem is that 230 and 250, that doesn't really get accounted for. So when you do a continuous versus a discrete, there's always going to be this like off because of the endpoint. So I said, all right, well, if the endpoint was a problem, let's make the interval just slightly below and slightly above. And that makes it more accurate, closer. Still wouldn't be it. But that's why it does approximation. All right, team. So that's 16E. So what to take out of 16E was that property. I'd like you to have that in your bound reference in the sense that if you ever see them ask you for an approximation normally, that's the first thing you're going to check. And then doing it is pretty much similar. So you can see how similar they both are. All right. That's 16E. I'm going to stop there. That's 50.